Hi everyone, today we are going through our next tutorial in LS Dyna to show how to use it in modeling. What we will have today, we are going to make a model for a car moving over a road, or we can use the same as for a train moving over a specific track. We will do this in LS Dyna, use what is called a trail and track model. I know maybe it's very advanced tutorial. We will go through a simplified tutorials later, but I do that because many of my friends asked me to do it. So let's go first. Our car is consists of a mass with 1e4, and this mass connected to the ground with a spring of 1e6 and of a damper with a damper of 1e4. And the mass located at 1 meter height from the ground, and the whole car or the whole train is moving with a constant speed of 1 meter per second. For the road is of 10 meter height, 10 meter length, and the road have no roughness over it. If we have a plan view for our problem, we will see that we have two wheels which represent our car. These two wheels is at a distance of 2 meter, and these two wheels is moving over the pole line, which is the track of the train or the road for my car. To do that in LS Dyna, we will go first through making our car and then making our track, and then show how to define the connection between the car and the track. So let's get started. First, what we want to do is to create the car. And to create this car, we are going to make it as a single degree of freedom system between two nodes. These two nodes will be this first one, which is located at the road. We will use the coordinate of x, y, z equal to 0. And the second node, where the mass is located, and this node will be at x, y equal to 0 and z equal to 1. So to do that in LS Dyna, first we are going to Element Tools and Node Editing to create the node, and I'm going to pick Create to create my nodes, and I'm going to create the first node, which is at x, y, z equal to 0. This is the lower point, and accept. And the second point is also at x, y, 0 and z equal to 1. So I'm going to create it at z equal to 1. This is my second point. Now, after creating the two nodes, I'm going to choose left view and auto center, and then I'm going to hold Control key and use your middle scroll, so you can see, you can make a zoom in and out. Also, if you hold your scroll button, you can make a pan for the view. And also, if you, instead of holding Control, you hold Shift button with the left mouse button, you can make a rotate for the view. So let's get back to our left view. These my two nodes, and between these two nodes I want to create a spring connecting this node to the other one. To make this system, we are going to define the section for the spring and the damper, and then we are going to define the material for the spring and the damper, and then create our element with this section and material. So to do that, we are going to the model and part, and then keyword manager, and in keyword manager I'm going to expand the all. And first, as I say, that we need to make a section for the spring and a section for the damper. This spring and damper is not as a beam or shear or solid element. They are called in LS Dyna as a discrete element. So we will go through a section, and you will find a specific section for discrete elements. So which is called discrete. So I'm going to discrete, and I'm going to define the spring section for my spring, and I'm click add, and I'm going to define a damper for my damper. Done. So now I have my section. What next? We want to define the material for the spring and the damper. And actually, someone ask, okay, we defined this section, but in the section definition we didn't define the spring coefficient or the damper coefficient. Actually, this will be defined in the material, not in the section part. So if you go to the material list and then you have to go down, you will find it at very low of the list. It's called S01. This is the spring material, and S02 is the damper viscous. This is for the damper. So first for the spring, I'm going to spring, and I'm going to name the material as a spring, and I'm defining the spring coefficient as 1e6 as what we have in our problem. Then I'm going to damper, and I name it as a damper, and also I'm defining the damping coefficient as 1e4 as we will have in our problem. So after we define the spring and the damper, the material of the spring of the damper, we want to define a part for a spring and a part for the damper. So we will put the material and the section of the spring in a part called a spring, and we will also put the material and the section for the damper in a part called a damper. So I'm going in the part list and open the parts, and first I'm going to name spring. This is my first part, and in the section ID I'm going to pick the spring section, and in the material ID I'm going to pick the material, spring material, and then accept. This is, I finished my spring definition. Then I'm going to click add and choose damper, add a damper name, and in the section ID I'm going to pick this damper section, and also in material ID I'm going to pick the damper material, and then I'm going to click accept. So this way I define my parts for the damper and the spring. What next? We want, now we have everything ready to create the spring between these two nodes and the damper also between these two nodes. And to create the spring and the damper, we will go through the element list. And then I'll scroll down until I reach a discrete element, which is my element. And first he asked me about the part. Okay, I'm going to create the spring first. And then he asks you here about a very important question. What your element is, what's the node that your element connecting between? So here I'm going to tell him that my element is connected between node number 1 and node number 2, which is this node, the first node, and the second node. If you inverse them, it's not a big deal. It will give you the same result. So I'm going to tell him that my spring connect between node number 1 to node number 2, and I'm going to click accept. This is my first element, which is the spring. I want to add another discrete element, which is the damper, so I'm going to click add. In the part ID I'm going to choose damper, and also the damper connect between node number 1 to node number 2, and I'm going to click accept. Done. And as you can see here, there's nothing exists in the view, right? Actually, this is an LS Dyna problem. So what we have to do to solve this is just a view problem. We have to save the file, close the LS Dyna, and open it again, and then you will see your model is ready. So that's what this is what I will do right now. I'm going to save it, and this is my model. And then I'm going to close the LS Dyna and open the file again. As you can see here we have our spring and damper. If you can see, you have the red line is the spring, it's a curly shape, and the damper is a dashboard system, it's the blue one. Now after we create the spring and damper, we will go to the next step that we already have the spring and damper. We finished modeling of these two elements. We want to create our mass. So to create our mass, we will go to the LS Dyna, and we'll go to the keyword manager, expand all list, and to create a mass you need to go to the element list, and scroll down until you will find the mass. And in the mass, he asks you about the node ID where you want to put your mass. So for our problem, we want to put a mass in the top, which is node number 2. And he asks you here about the mass value, so the mass is 1e4. And then accept. If I click done, as you can see here, the mass and the point in the top have been highlighted because there is a mass attached here. But for the bottom and the point in the bottom, there is no mass attached here. If we run the model in this case, when we finish the whole model and run it, we will have a problem with that because this node don't have a mass attached to it, and also this node is not constrained. It's not either constrained or have a mass attached to it. So it will be a problem for LS Dyna to run this model. So what we have to do to solve this problem, we have to attach a mass in this point, and we will use a very, very low value for the mass so it will not affect the whole result for the system. So I'm going again to mass and click add, and I want to add the mass for point number 1, and this mass will be of 1 kilogram second square per meter. Accept and done. And as you can see here, the lower point have been highlighted again. Let me just show our spring. I don't know why it have been vanished. I'll click OK. So now we have our spring damper system and we have the mass attached to it. What is the next step? We don't have only one wheel, we have 2 wheels. And to define these 2 wheels, we have to make another copy from this wheel at 2 meters in y direction. So to do that, we have 2 options. The first one is to repeat all these steps again at y equal to 2 meters, or to take a copy from the system, which is easier. So what we will do is we'll take a copy from the system, and to do that we are going to element tools and element transform, and you will find here translate, which we want to do. I want to translate it in y direction, which with a distance of 2 meters, and this distance will be in y positive, and I want to make a copy from the elements which you will move, and then I'm going to highlight my whole elements using area selection, and then I'm going to use translate positive. So when I do that, as you can see here, he have created another element at 2 meters in y direction. You may see a difference between these two, but if I click accept and done, then you have the second system exists exactly at 2 meters, and then we have the same properties of the first one. The third step, now we already finished our car model, it's ready to run. But now what we want to do is to make our road. And to define our road, we will define our road as a beam element, and this beam element will extend from this point until this point, which have a 10 meter width. So let's go down. This figure shows how we want to create our beam element. This is beam element, and this beam element extends from node number 1 to node number 2. And as we know that for beams we need to define what's called a third node. So LS Dyna will understand the directions of this beam. So we will create a third node at node number 2 with a z coordinate equal to 1.5 or 2 or whatever. You can choose whatever any coordinate you want. So in our case here, I'm going to create this node at z equal to 1.5. So let's go back to LS Dyna. To create the beam element, what we need first to create the nodes, and then after creating the nodes, we are going to create the beam. To do that, first I'm going to go through node editing, and I'm going to create a node at x0, y0, z0, which is this node, and accept. The second node, as shown here, will be at x equal to 0 and y0 and x equal to 10, which is the beam length, and z0 and y is equal to 0 too. So I'm going to create the second node at x equal to 10, y0 and z0. Create. As you can see here, this is my first node and here is my second node. If I make the left view, you will find this is my second node. Accept. After creating the second node, I want to create the third node, which is located at x equal to 10, y equal to 0, and z equal to 1.5 or 2 or whatever. You can choose any coordinate. So I'm going to put the third node as 10, 0, and z equal to 1.5. Create and accept and done. So this is my first node for the beam, this is my second node, and this is the third node which defines the direction of the beam. Now we want to create our beam element, which will represent the track or the road itself. To do that, we are going to use a different way from the one we described before in the videos. You can use any one of them. You can use the previous one, you can use this one. This one I think it's much way easier, so you can use any one of them. So I'm going through element editing. In element editing you will find create, so I'm going to pick from here create beam, and here he asks you about the nodes of the beam. So what you can do, I'm going to put the node, the first node here. Okay, I'm going to try to pick it. If I click here, you'll find that you have node 1, 3 and 5. Actually, let's have a 3D view for the beam so it will be much way representative. Again, if I click here, you will have node 1 and 5, and this is actual what we have here. We have node number 1, which is related for the wheel itself, which we don't want it, and we have node number 5, which have defined it lately for the beam itself. So I'm going to pick node number 5, and here I'm choosing node number 6, and here I'm going to choose node number 7. As you can see, he already created the beam, and I'm going to click accept and done. So this will represent my track, and as we did before, I'm going to use transform, and I'm going to pick this beam, I will choose here by element and choose a big selection, and I'm going to pick the beam, and then I'm going to make same as before. It's send y 2 meter, translate positive, and copy the elements. So translate and accept and done. So now we have two wheels which represent our car, our train, and we have our track. Now what we want to do is to define the track properties. So, and this track is a beam, so we will do exactly as what we did before. So I'm going to the keyword manager, and in the keyword manager, first I'm going to define a beam section for the beam, and then I'm going to define the material for the beam, and then I'm going to define the section and the material for this part which have been added in here. So I'm going through section, beam section, and I'm going to name this as a track. I'm going to choose element formulation number 4, same as before, and I'm just going to put a random track as 0.4, 0.4, 0.4, 0.4 dimensions, and accept. This is my track, and done. Now I'm going to define the material of the beam, so I'm going to material, and here I'm going to elastic, and I'm naming this as track 2, and I'm going to put a steel properties for this rail, and accept. Done. Now after we define the material of the beam and the section, we are go to through part, and you will find that there is a part have been added here, a new part, which is for the beam, related to the beam. This part called beam 3, I'm going to name it as a track, to change the name as a track. And for section ID, I'm going to pick the track, and for the material ID, I'm going to pick the track 2, and accept, and done. Now we have our model ready. What we have to do next is to define the constraining for this track. We want to make it fixed in the beginning and fixed in the end, and also we want to define the speed of the car. So we will be almost done with our model. So let's first define the boundaries of the track. To define boundaries, I'm going to close the keyword manager, because we are going to use entity, create entity. It's much way easier in creating the boundaries. And in the create entity, I'm going to click create, and then I'm going to choose boundary, SPC boundaries, and then I'm going to pick my nodes. So this is my first node, this is my second node, and here we have two nodes. So if I click, you will have a list which node you want. Actually what we want is node number 5, which is related to our track. And same if I click in here, you will have node number 3, this is related for the wheel, and node number 8, which is related for our track. So I'm going to pick node number 8. And the type of constraining, I'm going to constrain X, Y, Z, and the rotation in the 3 directions, and click apply. Actually, before we go ahead, there is a very important point here. Someone may ask that actually what we have, we don't have a beam element. What we have in the model, we have a road or a surface or a track. So if you define it as a beam, you will have a deflection in the middle, right? This is not true, because when we make our model, we will use the beam element as a one element. And because it's as a one element, so deformation in the middle is not allowed. So this will be representing as a road or as a track. So there is no problem with that. But if you divide this beam element into many points, in this case, this point you will start to have a deformation. This will represent, for example, a car moving over a bridge, not a car moving over a track. So let's get back again. Now we define the point, we make a constraining for these points. The second thing, we are going to restrain the whole system in Y direction. Why that? Actually, this spring damping system have a stiffness in one direction only, in the Z direction, and we want this system to move in the X direction. So if we have any kind of forces or loading in the Y direction, the solution will be invalid, because this system will fail. And to avoid that, maybe it will not happen, but to be sure that we will not have this problem, and to avoid that, we are going to restrain any movement in the Y direction. So what we want to do, sorry for that. So what we want to do is to restrain the movement in the Y direction. We don't want any movement in the Y direction. So I'm going to remove all the restraints. I'm going to create another restraint, and this time it's for the whole model, and I'm going to restrain the Y direction. There is no any movement in Y direction, and done. So this way I define the boundaries, the beginning and the ending of boundaries, and also I define the out of plane restrictions, so we will not have any problem of out of plane loading. Now what we want to do is to define the speed of the car, and to do that we will go again to the keyword manager, and we will go up in the boundaries. As you can see here, there is already a definition for the boundary. It's the SPC set, which defines the constraining for the beginning and the ending of the beam. Now what we want to do is to define a speed for our truck. To define a speed on our truck, we will have what we call the prescribed motion. In the prescribed motion, as you can see, we have a lot of definition for prescribed motion. What we can use in our case is what is called prescribed motion node or prescribed motion set. what is the difference between them. So let's go first in prescribed motion node. In prescribed motion node, you will put the node ID. In our case, we have this node and this node and this node and this node. Let's go out and know our node's number. If you want to know the node number, the element number, anything including that, you can go through element tools and you will find here identify. Let's clear the view first. If I open identify, you will find what you want to identify. Actually, I want to know the node number, and I want to know the node number by pick. If I go through this point, you will find it's node number 2. This is node number 4. And here you have 1 and 5, so I'm going to pick 1. And also, sorry for that, if you make a right click, you can make unselect for that. So if I'm going to, the list is not showing why. Yeah, I'm going to choose node number 3. So these are my nodes. I want to make all these nodes move with the same speed, which is equal to 1 meter per second. So let's go back to the keyword manager. And as I said, we have prescribed motion node. So what we will do in here, I'm going first to put node ID number 1. Okay, this node is going to move in degree of freedom. Which degree of freedom? If you go here in the list description, you will find that equation 1, if you put this equation equal to 1, it will be an X translation. If you put it at 2, it will be Y translation, 3, Z translation, and you have many other definitions. For our case in here, we want the car to move in X direction. This is my car and this is my road. So what I want to move it in X direction. So what I can do, I'm going to choose number 1, which is X direction. Now, what is the next step? The next step define what kind of movement you want to describe. Is it velocity, constant velocity, or constant acceleration, or constant displacement, or any other type of movement? In our case, we want a constant velocity. So to define a constant velocity, we want equation number 0, as it is set in here. Then after that, we're going to define load curve ID. How this speed is described through the time. To do that, I'm going to press the button in here, and here we ask you how you want to define your curve. I'm going to define my curve using new keyword manager. If I click that, he will open the keyword manager for the curves. So I'm going to pick curve. Here I'm going to name this curve as speed. For my speed is starting at 0 is equal to 1. I want the speed to be constant from the beginning of the run until the end. So at 0 is equal to 1, and at 100 or infinity is equal to 1. And accept. So this is my velocity curve. If I go again to my velocity curve, read and plot. So this show you how our curve is work. So at time equal to 0, the speed is equal to 1, and at 100 is equal also to 1. So I'm going to close this one and close this one too. And now he asks you about the scale factor or this velocity magnitude, which this is represent a scalar for the curve. So if I put a 10, he will times 10 times the curve, which is equal to 1. So it will be 10. If you put the curve, for example, you have a curve at 0 equal to 10 and at 100 equal to 10, and you put your scale factor as a 10 too, then the total will be 10 times 10 will equal to 100 meter per second. In our case, we have a speed of 1 meter per second, so I'm putting the scale factor as 1. And then I'm going to name the title speed of node 1 and accept. Then I'm going to define the second node, third node, and the fourth node. There's a much way easier way to define the speed using, instead of using the speed, defining the speed for each node, we can define the speed for a set of nodes. So how to do that? I'm going to delete this definition. Okay. And then instead of using prescribed motion node, I'm going to use prescribed motion set. In prescribed motion set, you will find almost the same definition, except here he is not asking you about the node ID. He asking you about the node set ID or the node group ID. To do that, I'm going to click in here, and here he asks you about if your node group is already exist or not. Actually, we didn't create any group for the cards yet, so we want to create another one. To create a group for the node of the cards, I'm going through new entity, and in the new entity I'm going to pick these 4 nodes. And I actually prefer to pick the nodes by ID. Don't pick them manually, because most likely, for example, if I pick in here, sometimes when you pick randomly you may pick a not valid node, so, and this will corrupt the whole solution. So it's much way better if you pick the nodes by ID. So what I'm going to do is just click node number 1, 2, 3, and 4, and here I'm going to name this as my car nodes, and I'm going to click apply. So here, if you see, this have been changed to car nodes, which is the 4 nodes that we have just defined right now. The remaining is same as what defined before. That here he asks you about the direction, it's x translation, and we wanted 0 because it's velocity. For the load curve, I'm going to open that. I will find my speed curve is already set in here, and the scale factor is equal to 1. The depth and birth you can define when, for example, if you don't want your car to start from 0 to the speed, or the car to start moving from 0, time equal to 0, you can define here when you want it to start to move. For example, if I put the birth equal to 3 seconds, then the car will stay constant until 3 seconds, and then will start to move. And also same for the depth. You can define when you want your car to stop from moving. By default, it will start from 0 and end in infinity. And here I'm going to name this as a speed of the car. And accept. Done. Now we want to define the load of the 2 masses in here, the on weight of the mass. To do that, we have two methods to define the load of the mass. The first one is to define the load as a on weight. This will be described later in later videos. We will not do it in here. And the other one we will do as before. We will put the load as a point load in node number 2 and node number 4. So I'm going to load, and you will find node point, and I'm going to put a load at node number 2 in degree of freedom 3. The load curve ID, I'm going to define a new load curve for the load, so I'm going to new keyword and in the curve, and for my loading I'm going to add a new curve, it's called load. And for the load curve I'm going to make it RAM, so at 0 equal to 0, and then at 1 equal to 1, and at 100 or infinity equal to 1, and then accept, and done. And here I'm going to define the load magnitude. The load will be of minus 1 to the power of 5 Newton, and accept. This is the first load. I'm going to add another one at node number 4, degree of freedom number 3, load curve, and minus 1e5. If you want to ensure that you have defined the load well, you can click draw, and then you can see your load with the magnitude in here. If I click all, then you can see the two loads in the nodes. Now we defined load on the two nodes. The final thing that we have to define is to define the contact between the car and the track. And to do that, this came to the title of our video, which is called Rail Track Model. And this is our rail track model. To do it, you will find a list called rail and track. So I'm going to rail. Actually, this have a lot of applications. It's not just restricted on representing a car moving over a track. For example, you can make this track as an imaginary part, and then you make the actual track as a solid element, and then you can move it over it. Or you can use this track, the path on a bridge, and this car is moving over the bridge. So it's not just a car moving over a track. It has a lot of application, and we will illustrate that in later videos. So we'll go in rail and track. You will have two lists here. First we will go through track. Here is the track ID. I will let LS Dyna to define it by itself. And here he asks you about the beam set ID for rail 1. Actually, if you go through rail and track, you have to define two tracks, and then correspondingly you have to have two wheels. There is no way you can define only one wheel or one track in using this method. So in here he asks you about the first track, and here asks you about the second track. So to do that, I'm going to click in this button to see how to define it. He asks you if you want to use the keyword manager or entity to make your beam set. I'm going to use my beam entity. And here what you have to do is just to click on this line, so he will understand that this is your first track. And in that, I'm going to define that as right track and apply. So this is the beam set for the first track, and now he wants the beam set which define the second track. So I'm going here and new entity 2, and then I'm going to pick the left beam, and this I'm going to name it as a left track and apply. Now after defining these two, the first track and the second track, the beam which represent the first track and the second track, the second thing he asks you about the node which located at the beginning of the track number 1 and node which is located at the beginning of track number 2. The node of the beam which exists at the beginning of the track. He's not asking about the car, he is asking about the beam. So this track start with node number 1. So if I go here, I'm going to close this one temporarily right now, no ignore definition, and make a clear view, and I'm going to node identify. So as we know, if I click in this point, I have two nodes. One is number 1, this node located at the wheel, it's not at the track, and node number 5 is located at the track, this one which the LS Dyna asked about. So I have this first node is node number 5, and if I hold button here, also I have node number 3, this located at the wheel, I don't concern about it right now, and node number 8 is located at the track itself. So this is my node. So what we will do here in the trail and track, again I'm going to pick the right track and this the left track, and here for the right track start with node number 5 and left track start with node number 8. After that, this load curve and offset and scale factor is to describe the track roughness. If you have, for example, some roughness of the road, or you want to define some roughness of the track, you can do it through these options. We will do this later in later videos. We will not do it in here. Actually, right now we have a smooth surface, so I'm going to accept it. I'm not going to define any roughness for the road. And done. This way we define our track. Now we want to define our train, which is our car, which is moving over the track. So I'm going to train, and in the train, the first thing is he asks you about the ID, the ID of this train. I'm not going to put it. I will let LS Dyna deal with that. Second thing, he asks you about the node set ID for the nodes in contact with the track, which mean for these two, for your train, which we have in here, our two wheels, what is the node which is directly in contact with the track? In this case, we have here node number 1, and here we have node number 3. So to do that, I'm going to click in here. You will not find any definition for these, so I'm going to click a new entity, and in the new entity I'm going to name this as a contact node between car and track. And this contact node will be node number 1, which is here, and node number 3, which is here. So as you can see, they have been highlighted. I'm going to click apply. So this way I define the node which is in contact with the track. And the second thing that you have to define is here is the track ID. Maybe for example you have many tracks in your model. So this one I'm going to define, I only have one track, which is number 1. And the final thing, he asks you about the vertical and lateral stiffness of your model. In our case, we are dealing with moving in X direction only, so we don't have a lateral stiffness, but we have a vertical loading, so we have to define the vertical stiffness. And the vertical stiffness, you have to put the elastic modulus of the material of the rail, unless you want to define it with any other different properties, because this represents an axial forcing over the track or the road itself. So for example, if you are making a model for the road, in this case you will put the elastic modulus for the bituminous material or for the asphaltic material. But if you are making a model for the track, you will put the elastic modulus of the steel material, which represent the track itself. Now if I click accept, this way I'm done by defining the connection between the car and the track. Now what we have to do, we almost done by all our definition. We just have to define the output. First I'm going to control and going down in termination. To define the duration of the run, I want it to spend 10 seconds. And then I'm going to database to define the output, and I'm going to pick binary D3 plot output, and I'm going to use a 0.01 between the runs. Before we end the run, let's make a run. So done. Now our model is ready to be run. Now what we want to do is to run the model. To do that, I'm going to save the model, and then I'm going to open my LS Dyna and choose my file. And this is my file, and I'm going to run it. Now what we have in here, if you see the output, you will find error termination, the model is not run, and this is logic. And let's try to know how to read the LS output. Here in the beginning you will find that he's reading your file, and from initializing complete, and then when he start to 128, this means that he start to solve your problem. And what we have is, if you can see here, that he solved, for example, for the first step when t equal to time equal to 0, the second step when time equal to this 0, when he go to the third step and fourth step, and after that he have a problem. The problem description is here, that he has out of range velocities. What does it mean by that? If you go to here, you'll find that the velocity of x and velocity of y is equal to 0.2 e31, which means it's very, very, very high velocity. Okay, and this is mean instability in the problem, and that's why the program stop of for solving the problem. So why we have this problem? If we let's try to understand how LS Dyna works. Actually, LS Dyna work using what's called an explicit solver. The explicit solver, simply, if you have, this is your time, the whole time of the run is 10 seconds. He divided the whole time into time steps, and he calculated these time steps by default. He's used have some formulas that calculate these time steps. What he do is, for each time step from these, he solved this system. If he found any instability problems, for example, that he found that to solve this system during this time step, he need that the velocity of this mass to be 1e31, 32, or whatever, then he found an instability problem for this model. Then he will stop the execution of the model. So how to solve this problem? To solve this problem, what we have to do is to reduce the time step. Instead of having very big time step, we have to reduce it. So to control the time step in LS Dyna, we will go here and go in the keyword manager and open the all tabs and go in the control, and you will find, if you go down, you will find time step definition. Here for time step definition, by default it's set as 0.9. This is the scale factor. He will time this scale factor by the time step value that he calculated by his formula. To solve this problem, I'm going to reduce it to 0.1, for example, and I'm going to see what will happen. So accept, done, and save the model. And then I'm going to save my model again. And then let's run the model again. So run the model. Okay, now as you can see, he's solving the problem, but we have to ensure that our model have been solved. So let's go back to the LS prepost, and I'm going to open file, open, and I'm going to open binary D3 plot file, and I'm going to open my D3 plot file to see the output. So this is my car and this is my track, and if I click play, here it works, but see what happens. The system is unstable. Actually, this is also related to the time step problem. This means the system is fails due to some error, we don't know. To ensure that we don't have any problem with our model, so I'm going to stop this model, file, new, no, don't save, new, yes, and then I'm going to open file, open keyword file, and now I'm going to change the time step to 0.01, and I'm going to save the model again, and let's run it and see what happens. Right now you see that you spend too much time because you decrease your solution accuracy, but hope so that we will have a good results. We don't know, maybe we don't have. Now it's done. Let's see the output file. So file, open binary D3 plot file, and open the value. And now let's run the model. As you can see, almost stable, no changes, no problem. So most likely, hopefully, we have a stable model right now until the end. To ensure also that we have a stable model, this displacement should be increasing and then vibrating around some static displacement. To do that and to see the displacement of this node, we will go through the output tab, and I want to plot the history of a node. And here, what he asked me, what do you want to plot? I want to plot a nodal history, and for this nodal history, I want to plot the displacement, and then I'm going to pick the node and plot. So as you can see here the displacement decreases and then start to vibrate around some static displacement. Actually, most likely, if you make some numerical model for this problem, you will find that this value is not too accurate too. So we still have to decrease our time step. Okay, let's see what we will have a change if we decrease the time step again. So file, new, yes, and I want to open file, open keyword file, and this time I'm going to decrease the time step again and make it 0.005. And then let's run the model again and see what we will have. For sure you will spend a longer time. It will be twice the time that we spent in previously, because we decreased the time step to half of the previous one, but hope that we will have a very good results. And maybe someone asks, okay, that there is no way to determine the time step except making trials. For sure there is some formulas. We will discuss this later, but it's a little bit complicated, so I prefer to make it just by trials, and you can see it's by third or fourth time you can reach the correct value. For sure, if you have very complicated model, then you have to ensure from the first one that you have picked the right time step. Now let's go to the LS open binary D3 plot file, and I'm going to plot again the nodal z displacement history for this point. Now I think all of you can see a very big difference between the previous and this one. This one is almost the accurate output for our system, that you have a decreasing displacement and then you have around the static displacement, which is 0.1 millimeter. You have a vibration, and this vibration reach almost to 0 after a while. And also if we plot the displacement of the lower node, you will have this excitation is due to the mass, that we have put a very small mass value. So for example, if someone want to make this output much way better, so what we can do, I'm going to open a new model again, and what you can do is to increase the mass in the lower point. And actually this mass is not affecting the solution, because you are putting the load in the top mass, so this mass most likely will not affect the solution. So what I'm going to do, I'm going to element mass, and for this mass I'm going to use as a 10 kilogram, and for the lower mass I'm going to use also 10 kilogram. Also you can make it 100, it's not a big difference, but more than 100, which is about 10% of the upper mass, I think it will start to have some contribution in the whole solution. So don't make it much more than 10% of the output of the upper mass value. If I'm going to run the model again, one of the benefits of increasing the mass value on the bottom, that the time to solve the problem will decrease, because the time step is function of the mass and the element length, and also the stiffness of the whole system. So if we increase the mass, you will find, you may didn't sense it right now, but you will find that the time to solve the problem will be much lower than the one before. I'm sure that just I put the right mass. Now let's see the output. And I want a nodal history, see displacement, flower node. So as you can see right now, we have, let's go first for the upper node. The upper node is displacement. Actually, if you compare it to the previous one, you'll find that the previous one, the mass was a little bit up there. So this value of the mass give you a better results, that it should be vibrating around the static displacement, which is equal to 0.1, and that's what we have exactly here. And for the lower node, due to we increase the mass, we don't have this noise that we have before. This noise actually is because of the mass inertia force is very low. So when you apply a load for the mass start to fly. But we have a small time step. The LS Dyna is reinforcing the mass to go back again to its stable position, so they stay constant. So to solve the problem with the vibration, you have two options. The first one is to reduce the time step much lower than what we have, or to increase the mass itself so it will have a little bit higher inertia force, so it will not start to vibrate a lot. And maybe someone asks, okay, why we have some displacement in the lower nodes? Actually, the lower nodes is just in contact directly to the surface of the rail. If you see the displacement value is it's equal to E minus Z, E minus 6. So it's very small value. But this displacement represents the deformation that will occur in the surface of the rail itself. And if you divided the force, which is 1 E6, by the elastic modulus of the steel, which is 2E11, we have 1 E6 by 2 E7. You will find that this value is equal to, 2E11. This is the elastic modulus of the steel, equal to 5.5 E minus 6, which is the value that we have in here. So this represents the deflection that will happen in the surface of the rail. Hope that you have gained good information from this video, and please, if you like it, just press like and subscribe in the channel. Don't just give me your feedback, and hope that the later videos will give you more information. Once again, I know this video is very advanced one. I just do it because many of my friends want to know how to make a rail track model. Later we are going to make some simplified models. We are going to through a simplified models again, through beam, shell, slab, solid elements, step by step, until we can reach making a full modeling using LS Dyna. Thank you.